Welcome back to this lecture series on pulse width modulation for power electronic converters. So, after initial about 7 or 8 lectures on power electronic converters, we have got started off with pulse width modulation. Our specific focus has actually been on voltage source converters. So, we have been looking at the pulse width modulation techniques for 3-phase voltage source converters, and today we will be discussing on low switching frequency PWM. The last couple of lectures we looked at the purpose of PWM and certain essentials for PWM such as the Fourier analysis and the harmonic the tools for calculation of harmonic currents, etc. Now we are trying to achieve the purpose of PWM, that is to control fundamental voltage and to mitigate the harmonics and their side effects, and we want to do this at low switching frequency. What is the low switching frequency? We are going to look at an inverter, and the inverter has devices, and these devices switch at certain frequencies now, and these frequencies are going to be very low. Why do we consider low switching frequencies? One reason is that at very high power levels, if you operate the inverter at you design an inverter for very high power level, then you cannot switch such high power devices at very high frequencies. Whenever you turn them on and turn them off, there is a certain amount of energy lost. So, the devices get heated up a lot. You cannot switch them beyond certain frequency. So, high power devices can generally be switched at lower frequencies. So, when you make high power inverters, you can only switch them at low frequencies. That is one reason. The second reason, and which is more important to us, is these low switching frequency methods help us learn certain essentials of pulse width modulation very well. We can develop certain amount of understanding, certain amount of insight and intuition, if we may venture to call so, by studying low frequency PWM methods. So, these are the reasons why we are venturing into that, and now let us see what we are trying to do. This is the voltage source inverter, 3-phase voltage source inverter. The 3-phase loads are connected to R, Y and B, and the DC supply is here. This is what has been our focus. In the next few lectures, we will certainly be dealing with pulse width modulation methods only for such 3-phase inverters now. And in this inverter, every leg is a single pole double throw switch as indicated here, and the single pole double throw switch is electronically realized as shown here. There are 2 IGBTs, and these IGBTs have anti-parallel diodes. So, they are capable of conducting in both the directions, as we have already said, we have seen several times. And when the top IGBT is conducting, the bottom IGBT will be blocking a voltage of this polarity, and the same thing vice versa. So, these devices have bidirectional current carrying capability and unidirectional voltage capability, and at the pole you can apply either this plus 0.5 VDC or minus 0.5 VDC measured with respect to the DC bus midpoint O. So, we defined pole voltages, and we defined the purpose of pulse width modulation. As we have already said, it is to control the fundamental voltage. What we want to do is we want to switch these converters, these devices within the inverter in such a fashion that for the given DC bus voltage, we want the desired fundamental voltage. We want the desired fundamental voltage on the AC side, and not just that, if possible and to the extent possible, we want to reduce the harmonic voltages and their harmful effects. This is what we want to do. So, the simplest way you can operate an inverter is a square wave mode, where let us call this as V or O, that is the R phase fundamental voltage. The R phase fundamental voltage varies like this, it switches from plus V to minus V at 0 and 180 degrees, it switches from positive to negative, and 360 degrees it goes back now. Alright. So, if this is supposed to be a square wave operation in an inverter, if the R phase leg is switching like this, that is the top device is conducting between 0 to 180 and the bottom is conducting between 180 to 360. How will the Y phase be? The Y phase is in such a fashion that 3-phase symmetry is satisfied. So, at 120 degrees, what happens is the Y phase goes high, it switches high from low. So, if this is 120 plus 180 is 300 degrees. So, at 300 degrees it comes back. So, this is 300 degrees. So, what I have drawn here is the Y phase pole voltage, that is the voltage at the midpoint of the leg Y measured with respect to the DC bus neutral O. So, this is the Y phase voltage which I have drawn with some greenish kind of color. Now, let us move on to see how the blue phase should look like. For convenience, let me choose blue color ink here. So, R phase switches from high to low at from low to high at 0, Y phase switches from low to high at 120. So, B phase should be switching from low to high at 240 degrees. So, this is 240 degrees. So, at 240 degrees the blue phase switches from low to high and it remains high for another 180 degrees, which is all the way plus 240 plus 180 is 420, up to 420 it continues to be high, and it is low for 180 degrees before 240, that is up to 60 degrees, that is up to 60 degrees, this is low, the Y phase is low. So, at 60 degrees it basically switches from high to low. So, this is how you have the 3 pole voltages. So, what you have here is VRO, that is, let me indicate it in red ink itself. This is the R phase fundamental voltage when you are considering square wave operation, and Y phase is shifted by 120 degrees and B phase is shifted by yet another 120 degrees. So, the 3 phases are really like this now. So, it is also called a 6 step mode. Why do we call it a 6 step mode? You can see that there are 6 different switchings here. Firstly, if you consider this first 60 degrees, you see that R phase is positive, R phase is positive. The next 60 degrees also R phase is positive, and again between 120 to 180 R phase is positive. Between 180 to 360 degrees the R phase is negative. This is what you have. Now, let me look at the yellow phase. Let me choose this yellow or one of these greenish colors, let me choose yellow. So, how about Y phase? The Y phase goes low to high at 120 degrees. So, between 120 to 180 degrees it is high. The same way between 180 to 240 degrees it is high, here also it is high. At 300 degrees it switches from high to low, and therefore, between 300 and 360 it is low. Similarly, between 0 to 60 and 60 to 120 it is low. Now, let us look at the blue phase. Let us look at the blue phase. The blue phase is high for the first 60 degree duration, and then the blue phase is low from 60 degree all the way up to 240 degrees it is low. Then what happens subsequently? It goes high. So, what I am trying to say is between 0 to 60 degree, this is between 60 to 120 degree, this is between 120 to 180 degree. So, every sixth of the fundamental cycle the inverter is in the same switching state. For if you consider 0 to 60 degree, it is in one particular switching state in which the top device of R phase is on, the bottom device of Y phase is on, and once again the top device of B phase is on. On the next switching 60 degrees, what happens? R and Y continue to be whatever they have been, they were. So, R top is high and Y bottom is gated high. Now, B just switches. So, this inverter state from what is plus minus plus, it now changes to plus minus minus, and once again it changes state, because who switches here at 120 degrees? At 120 degrees Y phase switches. So, from plus minus minus it moves on to plus plus minus. Again at 180 degrees R phase switches. So, plus which was R phase which was positive all along now becomes negative. So, plus plus minus here becomes minus plus minus here, and similarly you have the state minus plus plus between 240 to 300 and 300 to 360. So, it does not switch, it switches only once in 60 degrees and only one of the phases switches, and you see that there are 6 different intervals like this. During each interval there is one switching state. This is one reason why you may call this as a 6 step mode. Further, you can even draw the R phase, these are the pole voltages. You can subtract VRO and VYO and get your line to line voltage VRY. How will the line to line voltage VRY look like? If you look at the first 120 degrees, if you look at the first 120 degrees on this waveform, VRO is positive and VYO is negative. So, the difference VRO minus VYO is VDC by 2 minus of minus VDC by 2, therefore, it is equal to plus VDC. So, if you look at VRY, it is between 0 to 120, it will be plus VDC. And what happens between 120 to 180? VRO and VYO are equal, therefore, VRY is 0. Similarly, between 180 and 300, VYO is positive and VRO is negative. Therefore, VRY will be equal to minus VDC, and once again for the last 60 degree duration, VRY will be 0. So, what do you find? If you look at VRY, it will be 120 degrees. In the positive half cycle, it will you will find a positive pulse for 120 degrees, and similarly you will find a negative pulse. Let me just try sketching that here itself. So, this is what I am trying to do is VRY. I am sorry, let me okay. So, if I look at VRY, let me choose a color. Should I choose red? Yeah. So, VRY is going to be a positive pulse like this for 120 degrees, and then it is going to be 0 for the next 60 degrees, then it is going to be negative for the next 120 degree, and it is 0 again now. Then it goes high. This is what you have. So, this is what you have. So, this is how VRY looks. This is for 120 degrees, it is positive, and this is the 0 axis. Let me choose a different color to draw the horizontal axis. Yeah. So, this is the horizontal axis, and this is the vertical axis at time 0. So, this is high for 120 degrees. So, if you look at this, its fundamental is something like this. Its fundamental voltage will be something like this. So, for the first 30 degrees in the positive half cycle, VRY is 0, and the last 30 degrees in the positive half cycle, once again it is 0, and in the middle 120 degrees of half cycle, this is 120 degrees, VRY is going to be a positive pulse. The same way it is, you find this negative pulse for a 120 degree duration. This is how the VRY waveform looks like, and VYB will look similar, just shifted by 120 degree, and the VBR is also going to look like the same thing, further shifted by 120 degree. So, that is how you are going to look at. You can subtract VRY and VBR and scale them to come up with VRN. If you consider that the inverter is connected to, is feeding a balanced 3-phase star connected load, then you have the star to phase to neutral voltage VRN, VY and VBN. If you see them, they will be a 6 stepped waveform once again. So, during the first 60 degree duration, it will have a value of plus VDC by 3, and then it is 2 VDC by 3, then VDC by 3, minus VDC by 3, minus 2 VDC by 3, minus VDC by 3, and so on. That is the kind of nature of waveform that you will have for VRN. So, once again you see that every 60 degree the level changes. So, that is another reason. No, that is this is why you call it as a 6 step mode. So, it is either you call it square wave operation or you call it 6 step mode. This is the most fundamental method of controlling this. You cannot control the fundamental voltage here, you accept whatever fundamental voltage is. So, the fundamental component of the pole voltage is 2 VDC upon pi. So, the same is the fundamental phase to neutral voltage applied, it is of 2 VDC upon pi. Okay. So, now for controlling is where you need notches and all that, but the waveforms, all the waveforms we consider here have half wave symmetry, and when you say half wave symmetry, whatever value it has at theta, the same value it has at 180 plus theta with just a negative sign. So, this is half wave symmetry, and it ensures that there are no even harmonics. So, the PWM waveform has 3-phase symmetry, and it has half wave symmetry, and it also has quarter wave symmetry, which we have already discussed now. If it is quarter wave symmetry, you consider this 90 and 270 degrees, that is when the fundamental has its peak, that is when the fundamental has its positive peak, negative peak. So, about these, if you look at that, it has symmetry. So, if you move in this direction and if you move in that direction to same distance, you find that the waveform is identical. This is quarter wave symmetry, it makes your calculations easier. You need to consider only 1/4 of the waveform, maybe starting from 0 to 90 degrees now. So, that is what we are going to do now. What we are trying to do is, we are trying to control the fundamental voltage. So, we need at least one switching angle. So, we saw it in the last lecture that with one switching angle you can control the fundamental voltage, but you cannot influence the harmonic voltages, you have to accept whatever they are. So, now we want to be able to influence the harmonics to certain extent at least, and hence we go for 2 switching angles in a quarter. For two switching angles in a quarter, the complete pole voltage waveform looks like this. This is something we saw in last class. So, there are two switchings between 0 to 90, there is a notch. So, you do not have, because of half wave and quarter wave symmetries, it is unnecessary for you to draw the entire waveform. We can consider only the waveform starting from 0 degree to 90 degree, and its fundamental is something like this. Its fundamental is something like this. This is at 90. So, you are considering a quarter cycle of this waveform. This has two switching angles alpha 1 and alpha 2. So, this waveform is completely described by alpha 1 and alpha 2. What we mean here is we are considering a pole voltage, and the pole voltage is switching from negative to positive at 0 degree, and it has two switchings, one at alpha 1 switches high to low, and at alpha 2 it switches back from low to high, and till 90 degrees it has no switching, and it is symmetric about 90 and so on. So, since there are two variables here, this is the same thing drawn here. So, what we can do is the waveform is almost completely defined by alpha 1 and alpha 2. It is a family of waveforms. We are considering a family of waveforms, and for various pairs of values of alpha 1 and alpha 2. Okay. So, now to study this waveform, we can look at the switching plane now. Why do we want to look at the switching plane? Different pairs of alpha 1 and alpha 2 can lead to the same fundamental voltage. Let us say we want a particular fundamental voltage. That particular fundamental voltage is obtainable through several values of alpha 1 and alpha 2, several pairs of alpha 1 and alpha 2. One thing that we can first understand is what are all the values, the set of all pairs of alpha 1 comma alpha 2 that lead to a particular fundamental voltage. This is of interest to us. Alpha 1 comma alpha 2 is a set of all alpha 1 and alpha 2 that can give a particular value of fundamental voltage that we want, say 0.8 per unit or 0.5 per unit or whatever now. So, let us look at the whole thing in a switching plane where this is alpha 2 is taken on the vertical axis and alpha 1 is taken on the horizontal axis now. So, in this switching plane, we are not going to consider the entire switching plane, because alpha 1 is restricted, its range, it is not everything. So, alpha 1 if you take individually, alpha 1 can never go less than 0, and alpha 1 can never go greater than 90 degrees. So, alpha 1 is equal to 0. Let me choose red ink here, so that it will be clear on this. So, this is the line alpha 1 is equal to 0. This is the line alpha 1 equals 0 degrees, and this is the line alpha 2 equals alpha 1 is equal to 90 degrees. So, no switching angle will go beyond these two. We want these two switching angles within this region now. So, these are two limits now. Similarly, if you take alpha 2, you have 0 less than or equal to alpha 2 less than or equal to 90. Take alpha 2 alone, alpha 2 can never go less than. So, this line is alpha 2 is equal to 0 degree. Similarly, alpha 2 cannot go beyond 90 degrees also. So, this is alpha 2 is equal to 90 degrees. So, we need to look at only one quadrant and only one portion of this quadrant 90 etc., and that is not all, and alpha 1 and alpha 2 have some constraints again relating one another. What is that constraint? Alpha 1 has to be less than or equal to alpha 2, that is the constraint. If I put all the constraints together, it is actually 0 less than or equal to alpha 1 less than or equal to alpha 2 less than or equal to 90 degree. This is the constraint on the switching angles. So, this is the line alpha 1 is equal to alpha 2. So, you cannot operate at any value of alpha 1 lower than, any value of alpha 1 that is greater than alpha 2. So, if you look at it, you cannot operate in this side. Why? Alpha 1 cannot go less than 0. You cannot operate on this side of this line. Why? Because this line is alpha 1 is equal to alpha 2. You can operate only when alpha 1 is lower than alpha 2 and not otherwise. So, this is one. And the other thing is you cannot, your alpha 2 is maximum value is 90 degrees. So, if it is beyond 90, you are not going to consider that. So, this right triangle is the region of our interest. This is what we saw, and it is basically a kind of recollection on this now. All our waveforms are going to be within this now. So, what do we mean? Any point here is a PWM waveform. If I consider some point, this point has particular value of alpha 1 and particular value of alpha 2. Let me consider another point. Let me take yet another point. So, this point has a particular value of alpha 1, there is another value of alpha 2. So, this point is another PWM waveform of the type we are looking at. Let us take this. Here also it has some value of alpha 1 and some value of alpha 2. Let us take a point here, let us take a point there. So, all these points have some values of alpha 1 and alpha 2. All these are PWM waveforms of the variety we are looking at. Okay. So, now let us look at some specific examples as to how the pole voltage waveforms look like, how they look like. So, let me take this, take a point here. Okay. This is a point. Now, at this point it is 15 comma 30 degrees. I have considered the point 15 comma 30 degree, that is alpha 1 is 15 and alpha 2 is equal to 30. So, what is the PWM waveform? What is the pole voltage I am looking at? The pole voltage is like this. At 0 it switches from high to low, at 15 degrees it comes back, at 30 degrees it goes high, from 30 to 90 it stays high. This is 90 degrees. So, let us just simply work out a few more such examples now. Let us just work out a few such examples now. So, let me say consider another point. This point let me say is here. This is at 45, this is 45 comma 60 degrees now. 45 alpha 1 is 45, alpha 2 is 60. So, what you have is it switches from at 0 from low to high, and it is high at alpha 1 is equal to 45 degrees it comes down, and alpha 2 is equal to 60 it goes high. This is 45, this is 60 and this is 90. This is how this waveform is going to look like. Let me take yet another example. Let me say an example is here itself. This point is here. Let me call this point as C, or this is 75 comma 75. So, what is it that I am seeing? 75 comma 75, alpha 1 is at 75 degree, alpha 2 is also at 75 degree. That basically means there is no notch at all. So, this waveform is a square wave. So, in fact, this is the line alpha 1 is equal to alpha 2. You may consider any point on this line alpha 1 is equal to alpha 2. If you consider any point on this line alpha 1 is equal to alpha 2, you are going to have a square wave. So, this line corresponds to basically the square wave operation. So, you consider various points, you can just consider a few several arbitrary points here in different regions, and you can plot them, and you can just get feel for how the waveforms really look like now. So, this is some examples of pole voltage waveforms. Let us move to some special cases. The special case, one special case is something that I have already indicated, that is this line alpha 1 is equal to alpha 2. When alpha 1 is equal to alpha 2, you have it as a square wave, which we just saw. This is a square wave. At 0 degree it switches, and till 90 degrees it is high. This is a square wave. The other special cases that we have are, let us say, let us look at the line alpha 2 is equal to 90 degrees. This is alpha 2 is equal to 90 degrees. What do we mean by this? You have a PWM waveform. It switches like this. It switches from low to high at 0 degree. So, it switches down at alpha 1, but its alpha 2 is at 90 degree. Its alpha 2 is at 90 degrees. So, due to quarter wave symmetry, if there is a switching at alpha 2, there is another switching at 180 minus alpha 2. So, when alpha 2 is 90, there are two switchings at 90 degrees. That basically means there is no switching at all. Is that right? So, the waveform continues like this. The waveform continues like this. I am drawing it beyond this. So, this is 180 degrees, and this is 180 minus, this is 180 minus alpha 1. So, what happened to alpha 2? Alpha 2 became equal to 180 minus alpha 2 when they are 90 degree. When alpha 2 is 90 degree, alpha 2 is same as 180 minus alpha 2, and one notch has been removed from your waveform, from what is really this thing here, from the original waveform with two switching angles now. So, this is one special case. This is how the pole voltage looks like when you are operating on the line alpha 2 is equal to 90 degrees. The other special case that you can look at is when you are on the boundary of this plane, that is alpha 1 is equal to 0. So, the waveform by definition is supposed to switch from low to high at 0. Then it switches from high to low at 180 at alpha 1. If alpha 1 is 0, both of them happen at the same time. So, the waveform actually looks the other way. It is only at alpha 2 it goes high and then 90 degrees, it is like this. Then here this is 180 minus alpha 2, this is 180 minus alpha 2, it is like this, and at 180 degrees it switches high. This is how the waveform looks like. This is how the waveform looks like. This is 0 degree. So, you do not find alpha 1 at all, alpha 1 has merged with 0. So, this is again it looks like a third harmonic wave or whatever, the number of switching is less. Originally the waveform had 2 switchings per quarter cycle. In these two cases, when alpha 2 is equal to 90, instead of 2 switching per quarter cycle, it becomes only 1 switching per quarter cycle. Once again, when you have alpha 1 is equal to 0, instead of 2 switchings per quarter cycle, you have only 1 switching per quarter cycle. But these two waveforms at alpha 2 is 90 and alpha 1 is equal to 0 seem to have different phases, right. So, then you have the other case of alpha 1 is equal to alpha 2. When you have alpha 1 is equal to alpha 2, the number of switchings per quarter cycle is 0, because both of them coincide and there is no notch at all there, and so that becomes a square wave. So, these are the special cases of the pole voltage waveforms, and these special cases are basically what we are looking at is along the boundary of this permissible region of interest on the alpha 2 versus alpha 1 plane. So, these are the special cases of pole voltages where basically 2 switching per quarter gets reduced to 1 switching per quarter or 0 switching per quarter. Now, what does 2 switching per quarter mean in terms of switching frequency? You have 2 switchings per quarter cycle, and how many quarters are there? There are 4 quarters. So, this is 2 multiplied by 4, plus there are 2 switchings, that is 1 switching at 0 degree and 1 switching at 180 degree. So, a waveform totally switches 10 times, 2 times 4 plus 2, that is 10 times in a full cycle, and that divided by 2 is the number of switching cycles. So, this is 5. When a waveform switches with 2 switching angles per quarter, it is actually switching at 5 times the fundamental frequency. This is what is called as pulse number or sometimes. So, the number of the switching frequency to the fundamental frequency is 5 now. This gets reduced to 3 when alpha 2 is equal to 90 or alpha 1 is equal to 0, and this gets reduced to 1 if alpha 1 is equal to alpha 2. If alpha 1 is equal to alpha 2, it is a square wave, and if it is a square wave operation, it switches only at 0 degree and switches back at 180 degree. So, there is nothing that happens here. So, there are only 2 switchings in a cycle and only 1 switching cycle in a fundamental cycle. So, the pulse number or the ratio of switching frequency to fundamental frequency is 1 now. So, let us move on to see the phase of the fundamental voltage. That is what we are trying to see here is, we will again consider some examples now. Okay. First, let me consider one example that is here. This is quite similar to what I had taken, just a moment. Okay. So, let me consider alpha 1 is equal to 15 degrees and alpha 2 is equal to 30 degrees. This is the point I have considered now. So, let me put a circle around that, so that it is clear. So, how does the pole voltage look like? At 0, it switches from negative to positive, and at 15 degrees it switches back, and at 30 degrees it once again goes high. Then it is going to be high throughout till 90 degrees. Going to be high throughout till 90 degrees. So, this is how your waveform is going to be. This is for 15 to 30 degrees now. So, let me indicate the horizontal and the vertical axis on this clearly. Where is the horizontal axis? This is the horizontal axis, and where is the vertical axis? This is the time 0. It is like this now. So, let me consider another example. Let me consider another example where, shall I use a different color here? Okay. Let us say like this. This is something like 15 degrees comma 80 degree. Alpha 1 is 15 and alpha 2 is 80 degree. So, how will you have this waveform? It switches from low to high at 0 and high to low at 15, but it switches back only at 80 degrees here, and it is high till 90 and beyond. So, this is how this waveform looks like. What is the striking feature here? If you look at the fundamental component in the red waveform, the fundamental component is likely to be like this. It will have a 0 crossing here, but it will have a positive phase, it will be in phase with this now. On the other hand, if you consider this blue waveform, you see in the so called positive half cycle, in 1/4 of the positive half cycle, it is negative more often. Actually, the fundamental voltage could be something like this. So, the phase of this, it could really be out of phase, that is what we call as 0 degree in the red case is very well the positive 0 crossing of this fundamental sign, but what we call as 0 degrees here in the blue case is actually the negative 0 crossing of this phase now. So, what has caused the difference? The difference between alpha 1 and alpha 2 in the red point here, let me call the red point, this point as B, and let me call the red point as A. In case of point A, the difference between alpha 1 and alpha 2 is not very high, and it is more or less positive. The waveform is positive in the first quarter for most part of the time, and in the second case the waveform is more negative in the first quarter 0 to 90 degree. So, that is one difference that you find here now. You can take several such examples now. I can give another example, like let us say I may have my alpha 1 is 60 degrees, is 45 degrees, and alpha 2 is equal to 60 degree. This point I may call as A dash, and I may take another point which is say like here, the same 45 degrees and B dash. This is let us say the same 45 degrees as A dash, about 80 degrees now. So, you will find that this A dash is of the same variety here. So, the fundamental has the phase as indicated here, it is in phase, and here what you can call as out of phase. The fundamental phase is different. At 0 crossing, it is not at 0 degrees, it is not the positive 0 crossing of the fundamental, but it is the negative 0 crossing of the fundamental now. So, since you have quarter wave symmetry, you know you will have a 0 crossing of the fundamental there and of all the other harmonics there, but it is just a question of whether it is a positive 0 crossing or negative 0 crossing. So, these are some differences that you have now. So, in between these two, you must have a line somewhere there along which the amplitude is 0, the amplitude of the fundamental voltage is 0. Let us just look at that, because that could be the start of our exercise on controlling the fundamental voltage. Let us say I want the fundamental voltage V1 to be equal to 0. What is my V1? V1 is equal to 1 minus 2 cos alpha 1 plus 2 cos alpha 2. This is the fundamental voltage, I want it to be 0. Let us see what we can do to get this here now. So, let us do a few calculations to do that now. So, how can we obtain? One simple way to do this is substitute some value of alpha 1 and find out what is the value of alpha 2. So, you have 1 minus 2 cos alpha 1 plus 2 cos alpha 2 is equal to 0. This is your V1 and you want it to be 0 now. So, what is your alpha 2? Basically, your 2 cos alpha 2 is minus 1 plus 2 cos alpha 1, and what is your cos alpha 2 is half of that. Alpha 2 is basically minus half 2 cos alpha 1 divided by 2 and the cos inverse of this. And the cos inverse of this. So, cos alpha 2 is minus 1 plus 2 cos alpha 1 by 2, and you take the cos inverse, you get this now. Now, you can plug in several values of alpha 1 and you can get the corresponding values of alpha 2. Is that right? Okay. Let us come up with some values here. Let me take alpha 1 is equal to 0. It is a simple value to start. If I say alpha 1 is equal to 0, then what do I get here? Cos alpha 1 is 1. Therefore, it is 2 cos alpha 1 is 2. So, you have minus 1 plus 2 is 1, you have cos inverse of half. Alpha 2 is cos inverse of half, or you can say cos alpha 2 is 1 and 0.5 I am sorry. So, cos alpha 2 is, so minus 1 plus 1, this is, so it is half, and alpha 2 is cos inverse of 0.5, cos inverse of 0.5 is 60 degrees. So, if I consider alpha 1 is equal to 0, I want V 1 is equal to 0. If I consider alpha 1 is equal to 0, I get my corresponding alpha 2 to be 60 degrees. So, where is that? Let me go back to the previous curve. Let me say here, this is alpha 1 is equal to 0 and alpha 2 is equal to 60 degrees. This is the point I get now. Now, let me say another point, let me take another point. Very quick calculations are actually possible. If we consider, let us say alpha 2 is equal to 90, that is also a very easy place that you can come to. If I consider alpha 2 is equal to 90 degrees, then what happens is the 2 cos alpha 2 term is 0. Therefore, you get 2 cos alpha 1 is equal to 1. So, 2 cos alpha 1 is equal to 1 or alpha 1 is equal to 60 degrees, this is what you get. So, let us go back and see this point here, this is alpha 1 is 60 and alpha 2 is 90. So, these are the 2 points, I mean at which V 1 is equal to 0. I should not say these are the 2 points, these are 2 of the several points at which V 1 is equal to 0. So, let us say there are many other points. If we go on substituting values of alpha 1 in between, you will get corresponding values of alpha 2 from here, that is what we can do here. One simple value we will substitute is alpha 1 is equal to 30 degrees. When you substitute alpha 1 is equal to 30 degrees, so what you have is, you have your 2 cos alpha 2 and 2 cos alpha 2 is basically minus 1 plus 2 cos alpha 1, that is minus 1 plus root 3, is that right? It is minus 1 plus root 3. Alpha 1 is 30, therefore, cos alpha 1 is root 3 by 2, 2 cos alpha 1 is root 3. So, you have minus 1 plus root 3. So, this is 0.732. Therefore, your cos alpha 2 is something like 0.36, cos alpha 2 is something like 0.366 roughly, and your alpha 2 is going to be some value which is slightly higher than this 60 degrees, is that right? Is going to be some value like this. You can find out what is your exact value with your calculator and you can plug this in, you will find that it is coming somewhere like this. So, if you take several points in between, what you will find is, you will find you can get many such points like this, and you can join these points together and this will be your V 1 is equal to 0. So, this basically gives you the set of all points with this property of V 1 is equal to 0. That is, you consider any alpha 1 comma alpha 2, you consider any pole voltage with this value of alpha 1 and with such a value of alpha 1 and alpha 2, that pole voltage will give you 0 fundamental voltage tau. And if you go to this side, if you go to this side of this, take a point on this side, that is going to have a phase shifted waveform, the fundamental waveform is going to be out of phase. And if you consider on this side, as we saw before, this is going to be of proper phase. So, at omega t is equal to 0, what we call as omega t is equal to 0, the fundamental will have a positive 0 crossing, whereas in the blue case the fundamental will have a negative 0 crossing, and so this is the line along which you have 0 fundamental voltage now. So, let us say you want 0 fundamental voltage, it is slightly funny, I would like to clarify this. In most open loop VBF drives, you may not come to 0 fundamental voltage at all. You may start with some minimum fundamental voltage, it may be 2%, 3%, 5% or whatever it could be, it is not going to be 0 fundamental voltage. But there are closed loop situations where you may want 0 fundamental voltage to be applied or certain small amount of fundamental voltage to be applied, that is a different point now. So, why we consider 0 fundamental voltage is, there is a kind of continuity in the properties here. Now, let us say you consider this waveform that I have given here. If you say that the waveform has certain spectral properties at that point, in the neighborhood of that point the spectral properties are going to be quite close to it. So, let us say a particular harmonic is very high, or let me first say that the fundamental component of this point that I am indicating here is so much. Let us say it is 0.4 per unit, and if you want to consider somewhere in the vicinity of this, very close to it, again it will be very close to 0.4, it will be slightly higher or slightly lower than 0.4. Similarly, let me say that the fifth harmonic component of this point is very high, at this point is very high. So, you can say that in the neighborhood of this point, the fifth harmonic component will be fairly high. So, if you understand V1 is equal to 0, several operating points corresponding to V1 is equal to 0, you can reasonably understand V1 is equal. So, for the points at which V1 is some small value. So, if you want to consider V1 is equal to 0.03 or 0.05 etc., we can just start at V1 is equal to 0. Okay. So, now we have taken V1 is equal to 0, and all these points along this contour we have V1 is equal to 0. So, you need to be able to discriminate as what is a good operating point and what is a not so good operating point. So, what is good and what is bad about it is a situation now. So, we have to find out some examples for good quality waveform and some examples for poor quality waveform. So, what are good quality waveform, what are poor quality waveform? Okay. Let us look at some example here, go to points one by one. Let us say there is a particular point here, and let me call this point as A. This point let me call it as A. What is this point? This is alpha 1 is 0 and alpha 2 is equal to 60 now. Let me take that. Alpha 1 is 0 and alpha 2 is equal to 60. What is the nature of the waveform going to be here? And alpha 1 is equal to 0. So, at 0 the waveform is supposed to switch from low to high, and at alpha 1 is equal to 0 it is supposed to switch from high to low. Now, these two have been merged. So, the waveform is basically the other way here, and it switches high at alpha 2, this is 60 degrees and this is 90 degrees. This is how the waveform is. So, what is this waveform? Let us just come to that. What is this waveform? If I just continue this, at 120 degrees it will switch back, and at 180 degrees it will go back like this. So, what can you say about this waveform? This waveform has 0 fundamental voltage. Why? What is the frequency of this waveform? It has actually a periodicity of 100 and 120 degrees at the fundamental frequency. So, it is a third harmonic square wave. Its periodicity is 1/3 of the fundamental cycle. So, it is a third harmonic square wave. So, all those the frequency components it contains are 3 and odd multiples of 3. Why odd multiples of 3? It is a third harmonic square wave, and this waveform has half wave symmetry, and therefore, it does not have its own even harmonics, it has only its odd harmonics. So, the waveform contains n is equal to 3, 9, 15, 21, 27 etc. N is equal to 3, 9, 15, 21, 27 etc. It does not contain the other ones. So, the fundamental component is 0 here. Now, once again let me take another waveform here. Take, let us say, this particular point. Let me call this point as B. What is B? B is, you have alpha 1 is 60 and alpha 2 is 90. This is B. This is point B. So, at this point, if you look at the waveform switches like this. At alpha 1 is equal to 60, it comes back, and at 120 degrees it goes high. Alpha 2 is 90. Therefore, 180 minus alpha 2 is also 90. So, that notch is not there. So, it goes like this now. So, this is the horizontal line. So, this again is a third harmonic square wave, except that these two square waves are out of phase. This is also a third harmonic square wave. This also has n is equal to 3, 9, 15, 21, 27 etc. So, if you look at the line to line voltage, what is line to line voltage? VRY is going to be VRO minus VYO. VYO is phase shifted by 120 degrees, but these are all triplet frequencies. Any triplet frequency you phase shift by 120 degree at the fundamental frequency, it is going to be just identical. So, when VRO and VYO is subtracted from VRO, all the triplet frequency components are subtracted. So, essentially you will find that VRY is 0 throughout. So, there are no harmonics applied, it is 0 fundamental voltage and the harmonics are also 0. right. Now, what can be bad? Let us take something like this now. You take a point here, if you let me take about this is, I will call a point as C, and A is 0 comma 60 and B is 60 comma 90 and C is let us say 36 degrees. If you plug in 36 degrees, you will get 72 degrees as the output now. You would get 72 degrees as the alpha 2 here. So, if you do that, if you consider 36 comma 72, this is the point C. If you consider this, what will you get? At 0 the waveform switches, at 36 it switches back, at 72 it goes high. So, if 72 it goes high, this is 72 is 90 minus 18. So, at 90 plus 18 it will come down, 90 plus 18 is due to quarter wave symmetry is 108, and once again at 144 it will go high and 180 it will come low. So, this is the nature of the waveform. And what is this? What is this? This is a fifth harmonic square wave. The fundamental, the periodicity of this waveform is 1/5 of the fundamental cycle. So, it's a fifth harmonic square wave, it is a square wave, it is a fifth harmonic square wave. So, what are all the values of n it contains now? It does not contain a fundamental component at all, because its own period thing is 5. So, n is equal to 5, and further it has all it has no even harmonics, because it has half wave symmetry. So, it has its own odd harmonics, that is n is equal to 5, n is equal to 15, 25, 35 and so on. So, if you take the first two cases of A and B, and if you consider VRY, VRY will be 0, the fundamental voltage will be 0, and also the harmonic voltages will be 0, because these VRO contains only the third harmonics, and third harmonics get subtracted. Whereas, if you take this point C, if you take this, it is a fifth harmonic square wave. So, VRO has a fifth harmonic and VYO has a fifth harmonic, they are phase shifted by 120 degrees at the fundamental frequency. So, what you will get? You will get a resultant fifth harmonic in VRY. So, the waveform, that the voltage that you end up applying to the motor will be big fifth harmonic waveform. So, it is instead of applying some 0 fundamental or a very low value of fundamental, and what you end up applying is a very large amount of fifth harmonic wave. So, if you look at this V1 is equal to 0 curves, what turns out is these are the 2 points A and B, which are good points, good operating points. Why they are good operating points? The entire curve is capable of giving you 0 fundamental voltage, but at these points A and B, the harmonics are all 0. The harmonics are all 0. In all the other points, the harmonics are quite high. A particularly bad example is, yes, let me just check, this something like C, which is 36 comma 72 degrees is a particular, because it is a fifth harmonic square. We instead of what you want is 0 fundamental voltage and do not want any harmonics, you end up applying a large amount fifth harmonic in several points along this line, except if you are close to A or close to B, you are going to have fairly high harmonic content. Thus, we can distinguish between what could be a good operating point and what could be a not so good operating point here now. So, we have been focusing on V1 is equal to 0. If you just draw this again, V1 is equal to 0, what we got was, this was the curve V1 is equal to 0 we got. Roughly, this is the kind of V1 is equal to 0 we got. So, instead you want to get several other values of V1. Now, let us say what you want, V1 is equal to 0.2. If you want V1 is equal to 0.2, all that you need to do is V1 is equal to 1 minus 2 cos alpha 1 plus 2 cos alpha 2 equals 0.2. You substitute different values of alpha 1 and you get different values of alpha 2. So, your 2 cos alpha 2 is now 0.2 minus 1, 0.2 minus 1 is minus 0.8 plus 2 cos alpha 1, and your cos alpha 2 is the whole thing divided by 2, that is minus 0.4 plus cos alpha 1. I hope I am not making any mistakes here. So, it is 0.2, 0.2 minus 1 is minus 0.8, minus 0.8 plus 2 cos alpha 1, the whole thing divided by 2. So, your cos alpha 2 is minus 4 plus cos alpha 1, and you take the cos inverse of that, to get what you want. So, you plug in different values of alpha 1, you can get the corresponding values of cos alpha 2 and alpha 2, right. So, you can go about doing that. If you do that exercise, you can start with, for example, alpha 1 is equal to 0 degree. If you say alpha 1 is equal to 0 degree, it is easy to see cos alpha 2 is equal to minus 0.4. So, what we have is 1 minus 2 cos alpha 1 plus 2 cos alpha 2 is equal to 0.2. Therefore, 2 cos alpha 2 is 0.2 minus 1 here is minus 0.8 plus 2 cos alpha 1 and the whole thing divided by 2. So, what we have is minus 0.8 by 2 is minus 0.4 plus cos alpha 1. So, now let me substitute alpha 1 is equal to 0. When I say alpha 1 is equal to 0, what I have is 1. So, minus 0.4 plus 1 is basically 0.6. So, I made a mistake here, let me take this off. So, what I really have is So, what I really have is 0.6 now. Therefore, I will get some value of alpha 2, and where will that alpha 2 lie here on this curve? It will be somewhere here. This is cos alpha 2 is 0.5 and now I am talking of cos alpha 2 is equal to 0.6. So, it is some value lower than that here. This is the value that I will get now. So, if I go about getting several points, I will get points like this, and this would be my V1 is equal to 0.2. This curve could be my V1 is equal to 0.2. Similarly, I can get for any value of V1 that I really want. Let us say I want V1 is equal to 0.75. So, if I want V1 is equal to 0.6, maybe 1 minus 2 cos alpha 1 plus 2 cos alpha 2 equals 0.6. What I want, what I should be doing is, so here I will have 2 cos alpha 2 is equal to 0.6 minus 1 is minus 0.4 plus 2 cos alpha 1, and you divide this by 2, this is minus 0.2 plus cos alpha 1. So, you can once again plug in the values of different values of alpha 1 and you can get various values of alpha 2 now. So, you can do it for 0.6, 0.8 and anything that you want. So, if you look at something like 0.6 or so, you may get another curve like this. You may get a third curve, you may get more curves like this. So, these are higher and higher values of V1. So, V1 goes on increasing along this line, V1 is increasing. Similarly, when you come down this line, V1 is increasing, V1 is. So, I think I should better draw it this fashion. Let me take a red ink here. So, if I move in this direction, V1 increases. And what is my V1 along alpha 1 is equal to alpha 2 line? V1 is equal to 1 per unit. V1 is equal to 1, alpha 1 is equal to alpha 2 is a square wave, and therefore, that is equal to 1 per unit. So, you have several such constant fundamental voltage contours you can plot. You can plot not just for V1 is equal to 0. V1 is equal to 0 may be of very less practical significance, because you may not be applying V1 is equal to 0, but V1 is equal to 0.6 or anything 0.5, 0.8 etc. are more frequently applied. Let us say in a motor drive operating at a low frequency. So, you take those curves and many of these you can draw, this is how it is. So, from V1 is equal to 0 to V1 is equal to 1, for any value of V1 you can get curves here. If you go on this side, what you will get is, you will get negative values of V1 basically. That basically means the phase difference. So, whatever phase you get for fundamental and what you get there here will be out of phase, alright. So, now we have been able to come up with the several things to about the various contours for V1 is equal to 0.2, 0.5, 0.6 etc. we can draw. So, what it basically means is, if you want V1 is equal to 0.2, you have all these points available for you, and if you want some other value of V1 and you have several points available for you, let me take a different color and overdraw on this. So, you have several points, you can pick up any of those points. How to pick up one of those points? One thing you can do is to look at the harmonic content. So, pick up 1 or 2 of those points which have a better harmonic content than the others and use that. Okay, fine. So, we at least the choice in terms of V1 is becoming clear to us. So, there are several values of alpha 1 and alpha 2. that could give the same V1. We are first at least understanding what are the various values of V alpha 1 and alpha 2 that give us a particular value of V1, and then we can go on to select which value of alpha 1 and alpha 2 based on the harmonic content now, which is what we will do subsequently. So, in the constant fundamental voltage contours, what we had was, this is a kind of a curve. It will be interesting to understand the slope of this curve. Now, what we are saying is, we are looking at these curves V1 is equal to 1 minus 2 cos alpha 1 plus 2 cos alpha 2. This is equal to some constant, let me call this k. Now, I am interested in understanding the slope of these curves. So, what do? I can differentiate both sides with respect to alpha 1. So, what I will get here is 2 sin alpha 1 minus 2 sin alpha 2 times d alpha 2 by d alpha 1 is 0. This is what I get by differentiating both the sides now. So, what I essentially have is d alpha 2 by d alpha 1 is basically sin alpha 1 by sin alpha 2. This is what we get. This is what we get. So, the slope is something like this. The slope is something like that. So, the numerator is sin alpha 1, the denominator is sin alpha 2. So, whenever you have alpha 1 is equal to 0, you have alpha 1 is equal to 0, you can say that the slope is 0. You can say the slope is 0. Go back to the curves. You see that the slope is 0. The curves are practically flat here. There are some errors in drawing. If you actually plot them, you will find them, these are zeros here. You plot them, you can find out that they are 0. The slope is 0 there. Now, you go to the other side. You can go to the other side. What is that? You can say that, when is the slope going to be infinity? When alpha 2 for certain values of alpha 2 is 0, the slope will be infinity. Let me start from that. Slope equals infinity implies sin alpha 2 is 0. So, that means basically whenever alpha 2 is 0 or 180 or such values, it is going to be infinity. Is that correct? So, that is where you really have that there. Well, we should be careful in coming up to alpha 1 and alpha 2 both becoming 0. Anyway, you can see what happens here now. So, what I am trying to see is, before going to infinity, it is best that you go further on this curve. You find that, let us say this curve is 0 slope and the slope goes on increasing. The slope goes on increasing. What happens is, somewhere in the middle of the curve, the slope is, it looks flat. I mean, it looks more or less like a straight line now. So, if you consider this alpha 2 is equal to 90, if you take alpha 2 is equal to 90, if you take alpha 2 is equal to 90, then you say that the slope is equal to sin alpha 1. The slope is simply equal to sin alpha 1. So, sorry. Sin alpha 1. So, let us look at these curves. So, what is the slope of this curve at this point? It is simply equal to sin alpha 1. Again, if I take this point, what is the slope of that of the curve at that point? It is equal to sin of alpha 1. So, these are constant fundamental voltage contours. In the next lecture, we will be focusing on constant harmonic voltage contours, which will take us to selective harmonic elimination. Thank you and see you again in the next lecture.